Hey you guys, Lysandro here, and today I'm going to be covering a topic on chemistry, mainly on electrochemistry, and this is a particular process. I'm sure a lot of y'all that are focused on hydrogen technology or anything of the sort, any renewable energy, may have heard of this. And this process is called electrolysis. Okay, so basically, what electrolysis is electrolysis is the separation um, of elements through the application of electrical potential. It's basically putting electricity within a substance to separate it in its individual elements, individual ions. Okay, and one of the most common ones that y'all may have heard of is water electrolysis. And the way this goes is you apply any DC power source. It can be outlet or um, an outlet charger or a battery. Okay, and you have a negative terminal here, and on the other side you have your positive terminal. Okay, okay. So let's say this is a battery. You get your circuit, and you get one terminal at one side, and you get another terminal at the other side. And let's say you have a tank of water. Okay, okay. You have a tank of water. You have water here, and let's say, for example, you have two containers where the gas collects and all. Okay, and or whatever substance collects. Okay, what will happen is that when you flick on the power, um, an electrical current will go through here, go through the water and to the other end. But in the process, what it will do is, on one side, it'll collect hydroxide ions, okay, and on the other side, it'll collect the hydrogen ions, okay. Now, when it collects the hydroxide ions, um, what will happen is this. What happens is that because your positive terminal steals electrons, you'll end up producing um, you end up producing oxygen gas. Right here, the same. They're pretty much the same. You end up collecting a lot of hydrogen. You get hydrogen gas. You get oxygen gas. Okay, you get oxygen gas. Okay, and what these are is that this right here, this is your what they call your cathode. Your cathode. Okay, which is your positive terminal, and this is your anode, which is your negative terminal. And what these will collect is what you call um, cat ions, your cations, which are your negative ion, no, not your negative, your positive ions, and right here, vice versa, you'll collect your um, anions, okay, anions, which are your negative ions, okay. So that being the case, um, it'll collect this separately. Now, one thing that I want to make clear is this. Um, water water is not conductive, okay, and I'm talking about not not just regular tap water. I'm talking about 100% pure water, 100% pure H2O. Okay, 100% H2O. Okay, 100% H2O is not conductive. Okay, let's not. Does not conduct. Does not conduct electricity, and the reason why is that it's dielectric. Okay, meaning that it's is mostly an insulator. Okay. Okay. Also, another thing I wanna focus on is that water is also a polar molecule. Okay, it's a polar molecule, meaning that it has it's a polar molecule. Okay, meaning that it has its sides to which are negative. It has its sides which are negative and other sides which are positive. And I'll let you guess which ones are are positive and which ones are negative. You have okay, H, and your oxygen, which is O. Okay, and basically this side is your negative side, and this side is your positives. Okay, and because of this polar property of this molecule is also the reason why ice expands in volume when water expands in volume when it freezes, because of what they call intermolecular forces. Okay, let me erase this. Okay, okay, just enough to give you an idea of what I'm talking about. Okay, it's called intermolecular forces. Okay, okay, ice, water. Okay, which is basically inter it's an intermolecular forces. Okay, okay, it's primarily because of this this why ice tends to expand in volume. Okay, and you can explore this property, like for example, if you throw a salt on the water on the ice, it'll tend to melt because it'll disrupt this intermolecular force. Okay, and okay, but anyway, getting back to the whole deal with properties of water. Okay, another thing I want you to keep in mind is that ionic bonds require energy to break. And yeah, ionic bonds require high energy to break. Their ionic bonds are usually much stronger than covalent bonds because, for example, if you take any organic substance, it's kind of relatively easy to break those bonds. Um, in contrast to ionic bonds, if you were to take, like for example, an ionic compound like let's say salt, table regular table salt, okay, you would have to heat up um, you would have to heat up that salt almost near the melting point of steel. That's how much energy you would uh, require to break down salt. It takes a lot of energy to break the ionic bonds of salt. Okay, and getting back to the whole deal with salt is that when you put impurities, intentional impurities in water, um, what ends up happening is that you're making it easier for ions to travel, and what you have is what this all acts is an electrolyte. Electrolyte. Okay, and when you put it in the water, it acts as an electrolyte solution. Okay, which makes it easier for ions to travel within water. Okay, and you may have heard of electrolyte before, like for example, in Gatorade. Uh, in Gatorade, I don't know if you spell it that way, but and the reason why is because Gatorade, all these sports drinks, a lot of them they contain electrolytes. Uh, as a matter of fact, a lot of drinks contain electrolytes nowadays. Um, and the reason why is that electrolytes are an essential part uh, of our body. That's part of the reason why the nervous system operates the way it does, because it uses ions, like for example sodium. It uses ions like potassium, or it's just like chlorine or calcium. Okay, okay. It uses these in what they call ion channels. Okay, it uses these in ion channels which reside in our nervous system. So and it needs these vital ions. Okay, now and another thing that I want to say is this: um, whenever you another perspective I want you to keep in mind is this: whenever you put a salt, like for example, um, whenever you're putting anything ranging from, let's say, salts, like salts, acid, acids, bases, metal, metal ions, or metal metal oxides, you're basically putting electrolytes into a water solution. When you put any of these into water, you're putting electrolytes. Okay, and let me give you a perspective of what I mean. Okay, let's say for example you decide to add let's say H2O. Okay, you decide to add that to um, you decide to add to H2O regular table salt. Okay, of course, ignore the whole deal with the iodine they put in. Just regular table salt, pure regular table salt, NaCl. Okay, these are formula for salt, and this is a formula for water. Okay, okay, use something probably a lot of you don't know. Okay, HCl, which is um, hydrochloric acid, okay, plus um, sodium hydroxide, okay, produces this. And with sodium hydroxide, and this is what they call lye, or drain cleaner. Okay, so pretty much if you mix hydrochloric acid with drain cleaner, you end up with salt water. Salt water, otherwise known um, as brine. Okay, as brine um, or saline. Okay, okay. So keeping that in mind, there's certainly a lot going on with when you blend in salt and water. Okay, and what this is keep in mind this is acid and this is a base, a really strong base, if I may say. But yeah, acids base also always make water and salt. Make water and a salt. Okay, but this is just a little side detail I'm giving to kind of give an ideal idea behind the whole process of electrolysis. It's I guess like a little side note, but there are other types of electrolysis which um, do not require any form of water. And what those electrolysis are is pretty much you can only electrolyze in a molten state. And one of the applications for it is what they call bauxite. Okay, bauxite or aluminum oxide. Okay, aluminum oxide. Now, this is important for the production of aluminum, and the reason why is that basically what they do is that they melt this down till it's a liquid, and what they do is pass the same electrical potential um, through it to pretty much produce on one side aluminum and the other side oxygen. Okay. Okay. Being that the case is one it requires a lot of energy. Okay, and the way this works is pretty much um, you pretty much get a DC power source. Okay, you're seeing DC power source. Okay, the only difference here is that for mass production is a really high amount of DC power source, and what they do is they connect these to graphite terminals. Okay, they connect it to these okay. Okay, graphite. Uh, okay, so they connected to these graphite terminals. Okay, to these graphite terminals. Okay, and being that the case, what happens is that there's a lot of energy dumped in through here when it's in its molten state, and on one terminal it starts collecting aluminum, and the other one is collects starts producing oxygen and everything. So that's pretty much what happens and all. But there's a lot of other applications for electrolysis and everything. But I guess this would be all for now in regard to this portion of electrochemistry. But I guess I'll catch you guys next time. So anyway, please like and subscribe, and I'll see you guys next time. Bye.